Here's another relative motion problem that you're familiar with from previous physics courses. Just really simply a boat traveling across the river. Now the resultant motion of the boat is actually a vector sum. You've got to add the water motion to the motion of the boat when it's in the water. This is boat with respect to water. That little slash means with respect to. So you have to add those two together to get the overall motion of the boat relative to the ground. So it's a vector sum. And this is actually true for planes in the air, and it's actually true more generally as well. So the velocity of some object B is its velocity with respect to some other thing, some other frame of reference, plus the velocity of that frame of reference. And so the order here, B relative to A, as long as you follow that order, then this will be true. Now notice that if B is moving north relative to A, then A is moving south or opposite to that other direction. So BBA is the opposite of BAB. For instance, let's imagine that we have a car that's moving 40 kilometers an hour to the east. So here's our car, and it's going 40 to the east. And then we have a truck, and that truck is going 60 kilometers an hour to the north. And they're both headed towards the same intersection. There we go. And then what's the velocity of the car relative to the truck? What's the velocity of the car relative to the truck? That's what we want to find. Well, you can answer that one conceptually. Because if you're in the truck, then you see the car moving, well, first of all, 40 kilometers an hour towards that intersection point. And then since the truck's moving north towards the intersection seems to be coming towards the truck at 60. So since the truck's moving north to the intersection is moving south relative to the truck. That's really just what this point back here was all about, just that oppositely. So really simply then, it's just 40i, and if you use the usual coordinate system, where this is the y-axis and this is the x-axis, with that coordinate system, this would just be 40i minus 60j. Now, if we use our vector notation as another way of solving this, so velocity of car, velocity of truck, velocity of car with respect to truck. Since this is what we're looking for, we write the equation in this way. So car is 40i, truck was 60j. So solving for the velocity of the car relative to the truck, you're going to get 40i minus 60j, which is exactly what we got previously or above. Let's try another quick example. So here again, so here's a car, here's a truck. Find the truck relative to the car. So for that order, we're going to have the equation written this way. Truck velocity is car velocity plus velocity of truck with respect to car. Now we'll use the standard coordinate system where this is the y or j direction and this is x. So we use I and j there. So we see the truck is just 120j in kilometer per hour units. The car is going to be 80 cos 60i plus sine 60j. And then we can solve for the desired quantity, the velocity of truck with respect to the car, just by expanding this and bringing it over and then simplifying a little bit. So the I component, well, cos of 60 is a half, so that's half of 80, which is 40 minus 40i. And then the sine of 60 is root 3 over 2, so that's 40 root 3's. So 120 minus 40 root 3's ends up being 50.7 J, and that is in kph units. Now, there is a similar relationship to relate acceleration. So this is the relationship between velocities, so we can relate accelerations. Oops, that was a bit hasty. So A and B are frames of reference like the water and the ground, and this little a is the acceleration. Okay, so here's a problem for you to try. Here's a car, here's a truck, and we want the velocity of the car with respect to the truck, and then problem 12b will be the acceleration of the car with respect to the truck. So pause the video, try and work those two out, and then watch my solution. Alright, so here's the solution for you. So first of all, set up a coordinate system, and then better put vector signs on those. We want car with respect to truck, so we set the equation up this way, we get minus 12j in meter per second units. For the velocity, the acceleration, a little more tricky. We need to realize there's actually two accelerations for the car. There's a tangent acceleration due to the rate of change of speed, and then there's the normal acceleration, v squared over rho, inwards. Now, inwards in this case happens to be in the negative I direction, and tangent happens to be in the positive j direction at this instant pictured. So that gives this equation. Truck acceleration can just be directly substituted. And so you could solve for the acceleration of the car with respect to the truck, and that's in meters per second squared units. So there it is, the relative motion problem. Straightforward.